The Internals of Postgres. Chapter 11, Streaming Replication. The synchronous streaming replication was implemented in version 9.1. It is a so-called single master, multiple slaves type replication, and those two terms, master and slaves, are usually referred to as primary and standbys, respectively, in Postgres. This native replication feature is based on the log shipping, one of the general replication techniques, in which a primary server continues to send wall data and then each standby server replays the received data immediately. This chapter covers the following topics focused on how streaming replication works: how streaming replication starts up, how the data are transferred between primary and stand-up servers, how primary server manages multiple standby servers, how primary server detects failures of standby servers. Though the first replication feature, only for asynchronous replication, had been implemented in version 9.0, it had been replaced with the new implementation currently in use for synchronous replication in 9.1. 11.1. Starting the streaming replication. In streaming replication, three kinds of processes work cooperatively. A wall sender process on the primary server sends wall data to the standby server, and then a wall receiver and a startup process on standby server receives and replays these data. A wall sender and wall receiver communicate using a single TCP connection. In this section, we explore the startup sequence of the streaming replication to understand how those processes are started and how the connection between them is established. Figure 11.1 shows the startup sequence diagram of the streaming replication. So 1, start the primary and startup and standby servers. 2, the standby server starts a startup process. 3, the standby server starts a wall receiver process. 4, the wall receiver sends a connection request to the primary server. If the primary server is not running, the wall receiver sends these requests periodically. 5, when the primary server receives a connection request, it starts a wall sender process, and a TCP connection is established between the wall sender and wall receiver. 6, the wall receiver sends the latest LSN of standby's database cluster. In general, this phase is known as handshaking in the field of information technology. 7, if the standby's latest LSN is less than the primary's latest LSN, standby's LSN less than primary's LSN, the wall sender sends wall data from the former LSN to the latter LSN. Such wall data are provided by wall segments stored in the primary's pgxlog or pgwall subdirectory. Then, the standby server replays the received wall data. In this phase, the standby catches up with the primary, so it's called catch-up. 8, streaming replication begins to work. Each wall sender process keeps a state appropriate for the working phase of connected wall receiver or any application. Note that it is not the state of wall receiver or application connected to the wall sender. The following are the possible states of it: startup, from starting the wall sender to the end of handshaking; catch-up, during the catch-up phase; streaming, while streaming replication is working; and backup, during sending the files of the whole database cluster for backup tools such as PG base backup utility. The PG stat replication view shows the state of all running wall senders. An example is shown below. Select application name state from PG stat replication. As shown above, 2 wall senders are running to send wall data for the connected standby servers, and another one is running to send all files of the database cluster for PG base backup utility. Note: what will happen if a standby server restarts after a long time in the stopped condition? In version 9.3 or earlier, if the primary's wall segments required by the standby server have already been recycled, the standby cannot catch up with the primary server. There is no reliable solution for this problem, but only to set a large value to the configuration parameter wall keep segments to reduce the possibility of this occurrence. It's a stopgap solution. In version 9.4 later, this problem can be prevented by using replication slot. The replication slot is a feature that expands the flexibility of the wall data sending, mainly for the logical replication, which also provides the solution to this problem. The wall segment files, which contain unsent data under the pgxlog or pgwall, can be kept in the replication slot by pausing recycling process. 11.2. How to conduct streaming replication. Streaming replication has 2 aspects: log shipping and database synchronization. Log shipping is obviously one of those aspects, since the streaming replication is based on it. The primary server sends wall data to the connected standby servers whenever the writing of them occurs. Database synchronization is required for synchronous replication. The primary server communicates with each multiple standby server to synchronize its database clusters. To accurately understand how streaming replication works, we should explore how one primary server manages multiple standby servers. To make it rather simple, the special case, i.e. single primary, single standby system, is described in this section, while the general case, single primary, multiple standby system, will be described in the next section. 11.2.1. Communication between a primary and a synchronous standby. Assume that the standby server is in the synchronous replication mode, but the configuration parameter hot standby is disabled and wall level is archive. The main parameter of the primary server is shown below. So synchronous standby names, standby 1, hot standby is off, and wall level is set to archive. Additionally, among the 3 triggers to write the wall data mentioned in section 9.5, we focus on the transaction commits here. Suppose that one backend process on the primary server issues a simple insert statement in auto-commit mode. The backend starts a transaction, issues an insert statement, and commits the transaction immediately. Let's explore further how this commit action will be completed. See the following sequence diagram. 1. The backend process writes and flushes wall data to a wall segment file by executing the functions xloginsert and xlogflush. 2. The wall sender process sends the wall data written into the wall segment to the wall receiver process. 3. After sending the wall data, the backend process continues to wait for an ACK response from the standby server. More precisely, the backend process gets a latch by executing the internal function sync rep wait for LSN and waits for it to be released. 4. The wall receiver on standby server writes the received wall data into the standby's wall segment using the write system call and returns an ACK response to the wall sender. 5. The wall sender flushes the wall data to the wall segment using the system call such as fsync and returns another ACK response to the wall sender and informs the startup process about the wall data updated. 6. The startup process replays the wall data, which has been written to the wall segment. 7. The wall sender releases the latch of the backend process on receiving the ACK response from the wall receiver, and then backend processes commit or abort action will be completed. The timing for latch release depends on the parameter synchronous commit. If it is on default, the hatch is released when the ACK of step 5 is received, whereas if it is remote write, it is remote write when the ACK of step 4 is received. Note: if the configuration parameter wall level is hot standby or logical, Postgres writes a wall record regarding the hot standby feature, following the records of a commit or abort action. In this example, Postgres does not write the record because it's archive. Each ACK response informs the primary server of the internal information of the standby server. It contains 4 items below. 3 LSN locations of the latest wall data, where it has been written, where it has been flushed, and where it has been replayed in the startup process. Additionally, it holds the timestamp when this response has been sent. Wall receiver returns ACK responses not only when wall data has been written and flushed, but also periodically as the heartbeat of the standby server. The primary server therefore always grasps the status of all connected standby servers. By issuing the queries shown below, the LSN-related information of the connected standby servers can be displayed. Select application name as host, write location as write LSN, flush location as flush LSN, replay location as replay LSN from PG stat replication. Note: the heartbeats interval is set to the parameter wall receiver status interval, which is 10 seconds by default. 11.2.2 Behavior when a failure occurs. In this subsection, descriptions are made on how the primary server behaves when the synchronous standby server has failed, and how to deal with this situation. Even if the synchronous standby server has failed and is no longer able to return an ACK response, the primary server continues to wait for responses forever. So, the running transactions cannot commit, and subsequent query processing cannot be started. In other words, all of the primary server operations are practically stopped. Streaming replication does not support a function to revert automatically to asynchronous mode by timing out. There are 2 ways to avoid such a situation. One of them is to use multiple standby servers to increase the system availability, and the other is to switch from synchronous to asynchronous mode by performing the following 2 steps manually. Step 1, set empty string to the parameter synchronous standby names. And step 2, execute the PG control command with reload option. The above procedure does not affect connected clients. The primary server continues the transaction processing as well as all sessions between clients and the respective backend processes are kept. 11.3. Managing multiple standby servers. In this section, the way streaming replication works with multiple standby servers is described. 11.3.1. Sync priority and sync state. Primary server gives sync priority and sync state to all managed standby servers and creates each standby server depending on its respective values. The primary server gives those values even if it manages just one standby server. Haven't mentioned this in the previous section. Sync priority indicates the priority of standby server in synchronous mode and is a fixed value. The smaller value shows the higher priority, while 0 is the special value that means in asynchronous mode. Priorities of standby servers are given in the order listed in the primary's configuration parameter synchronous standby names. For example, in the following configuration, priorities of standby 1 and standby 2 are 1 and 2 respectively. Standby servers not listed in this parameter are in asynchronous mode. Their priority is 0. Sync state. Sync state is the state of the standby server. It is variable according to the running status of all standby servers and the individual priority. The following are the possible states. Sync. Sync is the state of synchronous standby server of the highest priority among all working standbys, except asynchronous servers. Potential. Potential is the state of spare synchronous standby server of the second or lower priority among all working standbys, except asynchronous servers. If the synchronous standby has failed, it will be replaced with the highest priority standby within the potential ones. Async. Async is the state of asynchronous standby server, and this state is fixed. The primary server treats asynchronous standbys in the same way a potential standby, except that their sync state will never be sync or potential. The priority and state of standby servers can be shown using the following query. Select application name, sync priority, sync state from pgstat replication. Note: several developers are recently trying to implement multiple synchronous standby. 11.3.2. How the primary manages multiple standbys. The primary server waits for ACK responses from the synchronous standby server alone. In other words, the primary server confirms only synchronous standbys, writing and flushing of wall data. Streaming replication, therefore, ensures that only synchronous standby is in the consistent and synchronous state with the primary. Figure 11.3 shows the case in which the ACK response of the potential standby has been returned earlier than that of the primary standby. There, the primary server does not complete the commit action of the current transaction and continues to wait for the primary's ACK response. And then, when the primary's response is received, the backend process releases the latch and completes the current transaction processing. The sync state of standby 1 and standby 2 are sync and potential, respectively. 1. In spite of receiving an ACK response from the potential standby server, the primary's backend process continues to wait for an ACK response from the synchronous standby server. 2. The primary's backend process releases the latch, completes the current transaction processing. In the opposite case, i.e. the primary's ACK response has been returned earlier than the potential's one, the primary server immediately completes the commit action of the current transaction without ensuring if the potential standby writes and flushes wall data or not. 11.3.3 Behavior when a failure occurs. Once again, see how the primary server behaves when the standby server has failed. When either a potential or an asynchronous standby server has failed, the primary server terminates the wall sender process connected to the failed standby and continues all processing. In other words, transaction processing of the primary server would not be affected by the failure of either type of standby server. When a synchronous standby server has failed, the primary server terminates the wall sender process connected to the failed standby and replaces synchronous standby with the highest priority potential standby. See Figure 11.4. In contrast to the failure described above, query processing on the primary server will be paused from the point of failure to the replacement of synchronous standby. Therefore, failure detection of the standby server is a very important function to increase availability of replication system. In any case, if one or more standby server shall be running in synchronous mode, the primary server keeps only synchronous standby server at all times, and the synchronous standby server is always in a consistent and synchronous state with the primary. 11.4 Detecting failures of standby servers. Streaming replication uses two common failure detection procedures that will not require any special hardware at all. 1. Failure detection of standby server process. When a connection drop between wall sender and wall receiver has been detected, the primary server immediately determines that the standby server or wall receiver process is faulty. When a low-level network function returns an error by failing to write or read to the socket interface of wall receiver, the primary also immediately determines its failure. 2. Failure detection of hardware and networks. If a wall receiver returns nothing within the time set for the parameter wall sender timeout, default 60 seconds, the primary server determines that the standby server is faulty. In contrast to the failure described above, it takes a certain amount of time, maximum wall sender timeout seconds, to confirm the standby's death on the primary server, even if a standby server is no longer able to send any response by some failures, e.g., standby servers, hardware failure, network failure, and so on. Depending on the types of failures, it can usually be detected immediately after a failure occurs, while sometimes there might be a time lag between the occurrence of failure and the detection of it. In particular, if a latter type of failure occurs in synchronous standby server, all transaction processing on the primary server will be stopped until detecting the failure of standby, even though multiple potential standby servers may have been working. Note: the parameter wall sender timeout was called replication timeout in version 9.2 or earlier. Whoo! All right. So we're done. That's it, folks. Cheers.